Prep 8, Multiple Linear Regression. In this module, you will learn how to conduct a multiple regression analysis in Excel using either the all-at-once method or the stepwise method. You will also learn how to conduct an analysis with both qualitative and quantitative predictor variables. You will also learn how to interpret the output from the analysis, as well as how to create and use the regression equation. If you remember, regression analyses allow us to predict or estimate a variable. Simple regression uses one variable to predict another variable, whereas multiple regression uses multiple variables to predict a variable. In order to conduct a multiple regression, the relationship between each x and y variable must be linear. In addition, while the predictor variables can be either qualitative or quantitative, the predicted variable, the y variable, must be quantitative. If your y variable is qualitative, you would have to conduct a logistic regression. This is an advanced statistical method, and it will not be covered in this class. Just like simple regression, a multiple regression analysis will tell us if we can actually predict y with our predictor variables. The analysis will indicate which of the x variables significantly predict y, and if there are any that do not predict y. In addition, the analysis will create an equation that we can use to predict future cases of y. If you look at the first tab on your prep file, you can see that we're going to conduct a multiple regression analysis to see if we can predict the cost of heating a home in January. We're going to use the average outside temperature, the inches of insulation in the attic, and the age of a furnace. And in order to do that, I'm going to go to the Data tab and open up my Data Analysis Toolpack. I'm going to select Regression and hit OK. First, we have to select the y variable. Again, the y variable is the variable that we want to predict, so that would be cost of heating a home. Highlight the data, including the heading. The x range is going to be the x variables. So I'm going to highlight all of the data for our three predictor variables. When you do a multiple regression analysis in Excel, all of the predictor variables have to be next to each other, so you can highlight them all at once. I'm going to select labels, and that's because I included labels when I highlighted the data. And for the output range, I am going to click on the designated cell, which is right here where it says place full model here. And then I'm going to hit OK. Hit OK again. Here is the output from the regression analysis. Just like in simple regression, we are going to first do the global test. If you remember, for the global test, we do the p-value approach. So if the p-value is greater than 0.05, that indicates that our x variables do not significantly predict y. However, if the p-value is less than or equal to 0.05, that'll indicate that at least one of the x variables significantly predicts y. Here is the p-value for the global test, and it has the e negative 0.06. This is scientific notation. This indicates that this is actually a really small number. And if you see in the formula bar, you can see that it's actually a really small number. So we typically report this as p is less than 0.001. And you can see that our p-value is less than 0.05. So that means at least one of our variables significantly predicts cost. So it could be the case that all three variables predict cost. It could be the case that two of the variables predict cost, but we know that at least one variable predicts cost. In order to figure out which variables significantly predict y, and if there are any variables that do not significantly predict y, we have to do the test for the individual coefficients. And again, we're going to use the p-value approach. So if the p-value for that specific variable is greater than 0.05, that indicates that that variable does not predict y. Typically, we'll refer to that variable as non-significant, so you'll hear me say that term a lot. So again, if the p-value is greater than 0.05, x does not predict y, and it's considered to be non-significant. If the p-value is less than or equal to 0.05, that indicates that the x variable does significantly predict y, and then the variable is referred to as significant. Now we can do the test for the individual coefficients. You can see temperature. Here's the p-value. Again, it has that scientific notation, that e negative 0.05. If you look up here, you can see that it's a really small value. So this p-value is less than 0.05, so that means temperature significantly predicts cost of heating a home. So that variable is considered to be significant. I'm going to highlight it in green, and that's because, yes, it is significant. If you go to insulation, our second predictor variable, you can see the p-value is 0.0066. This is less than 0.05, so this variable is significant as well, or in other words, insulation significantly predicts cost. So I'm going to highlight that in green. So our first two variables are significant. If you look at age, here's the p-value. Our p-value is 0.148 if you round to 3 decimal places. This is greater than 0.05. So this means that age does not significantly predict cost. So this variable age is considered to be non-significant. So I'm actually going to fill it with red. It's not significant. It's not significant. So you can see 2 out of the 3 variables significantly predict cost of heating a home. However, the regression model that's used for prediction can only include significant predictor variables. So we can't use that analysis to create the regression equation, and that's because one of the variables, age, was not significant. It didn't significantly predict cost. So what we need to do is we need to eliminate that variable. So anytime you do a multiple regression analysis, you have to use a method to eliminate non-significant variables if you have non-significant variables. And there's 2 methods that you can use. In this video, I'm going to show you how to use the all-at-once method. In the next video, I'll show you how to use the stepwise method. The all-at-once method is simple and straightforward. You need to conduct a second analysis, however, you exclude all of the variables that were non-significant in the first analysis. That is, the second analysis only includes the variables that were significant in the first analysis. Very rarely, you'll have to repeat the procedure. In rare cases, there will be variables that become non-significant in the second analysis. If that happens, you will need to conduct a third analysis in which you remove those variables. However, more often than not, all of the variables will be significant in the second analysis. In our example, age was not significant. So we're going to conduct a secondary analysis, and we are going to exclude age from that analysis. I'm going to open up the data analysis toolpack, select regression, and hit OK. My y range is the same, the y variable is the same, however, the input for the x range is going to be different, and that's because I'm going to exclude age. So I'm just going to highlight temperature and insulation. The output range is going to change as well. So I'm going to click on the specially designated cell, and then I'm going to hit OK. OK again. So first we have to do the global test. You can see that it's a very small number. It has that E -6, so the p-value is less than 0.001. It's less than 0.05, so that indicates at least one of the predictor variables significantly predicts cost. So it is significant. And now we can go and look at our individual predictor variables and see which ones are significant or predict cost. And you can see that temperature is significant, so the p-value is less than 0.05, as is insulation. So both of these variables are significant. They both significantly predict cost. Now I'm going to answer some of the questions. So for the final model, what was the p-value for the global test? And again, it was less than 0.001. So again, whenever we have a p-value that's less than 0.001, we report it as less than 0.001. The second question asks if temperature was included in the final model, and yes, temperature was significant, as was insulation. However, age was not. So if you remember in the first analysis, it was non-significant, so we excluded it from the final model. So the final model in regression for multiple regression is the model in which all of the predictor variables or the x variables are significant. So this would be our final model, and this is the model that we would use for prediction. And it's also the model that we would use for the regression equation, which is the next question. Here's the regression equation for multiple regression. You can see that it's very similar to the equation for simple linear regression. This boxed area was the equation that was for simple linear regression. Again, y hat is the predicted value of y, b sub 0 is the y-intercept, B1 is the slope for the predictor variable, the first predictor variable. X1 is the first predictor variable. So the equation for multiple regression just includes the slope and the second predictor variable. So the slope for the second predictor variable and the second predictor variable. And then you would just continue that on depending on how many predictor variables you have. As a reminder, the y-intercept tells us the predicted value of y when x is 0. Since this is multiple regression, we have multiple predictor variables. So the y-intercept tells us the predicted value of y when all of the predictor variables in the model have a value of 0. The slope tells us the predicted change in y if x increases by 1 unit. The sign of the slope tells us the relationship between x and y. So if the slope is positive, that means there's a positive relationship. So if x increases by 1 unit, y will increase as well. If the slope is negative, that means there's a negative relationship. So if x increases by 1 unit, y is predicted to decrease. If you return to your start file, we'll create the regression equation for our example. The regression equation is y hat, or the predicted value of y, so that would be predicted cost, equals the y-intercept. Our y-intercept is 490.29, plus the slope for the first variable, which is negative 5.15, times the x variable, which is temperature, plus the slope for the second variable, which is negative 14.72, times the x variable, which is insulation. So this is our regression equation. So again, the y-intercept is the predicted value of y, or cost, when both variables are 0. So if the average temperature is 0 and there's 0 inches of insulation in the attic, then the average cost of heating a home would be $490. The slope for temperature tells us the predicted change in cost when temperature increases by 1 degree. So cost is expected to decrease, that's because we have a negative sign, by $5.15 for every increase in 1 degree in average temperature. The slope for insulation is negative 14.72. So that means for every additional inch of insulation in your attic, your heating cost in January is predicted to decrease by $14.72. If you return back to the question, we can indicate what's the final regression equation. And that would be option C. The next question asks, what percentage of the variability in heating costs can be explained by the final regression model? This question is asking what R squared is. So if you return to the output for the final model, always make sure that you refer to the final model. We can see R squared. When you conduct a multiple regression analysis, we don't use the R squared, we use the adjusted R squared. So our answer would be 74.95%. So this means 74.95% of the differences in a home's heating cost can be explained by the differences in the average temperature and the amount of insulation in the attic. The next question asks, on average, how much air is associated with the predicted heating cost? This question is asking about the standard air. Here is our standard air. It's 52.98. So that means, on average, our predictions for heating cost are going to be off by $52.98. Now I'm going to complete the final model summary table. I'm going to do this by referencing the cells in the output. First, I'm going to indicate what the intercept is. Next, I'm going to indicate the slope for temperature. and the slope for insulation. Age was not in the final model, so anytime you have a predictor variable that's not in the model, you're just going to write NA. So I'm going to write NA for both the slope and the p-value, and that's, again, because age was not in the final model. Next, we want to do the p-value for temperature. The p-value for temperature was less than 0.001. So what I'm going to do, as it states in the instructions, I'm going to report it as less than 0.001. The p-value for insulation was 0.008. So I'm going to reference that. Finally, I'm going to complete the prediction table. So I'm going to use the regression equation to predict the average heating costs for these three homes. So the regression equation would be equals the y-intercept, and I'm going to lock that, plus, and then in parentheses, the slope for temperature, which needs to be locked, times temperature, end parentheses, plus, and then in parentheses, the slope for insulation, locked, times insulation. So we get 221.73. So here is the predicted or estimating heating costs for these three homes. There is an alternative way that you can set up the regression equation in Excel. So this would be equals the y-intercept, which again needs to be locked, plus, and then what you can do is you can utilize the sum product feature. So first what we can do is we can indicate the two slopes. So I highlighted that. We're going to want to lock that. And then, comma, and then I can highlight the data. So what this sum product function does is it's going to take the slope for temperature times the temperature, and then it's going to add it to the product of the slope for insulation times insulation, which is exactly what we want to do. And you can see that the final result is the same. So this is just an alternative way that you can write a regression equation in Excel to predict your y variable. In the next video, we'll do another multiple regression example, and I'll show you the stepwise elimination method.